Hello, and thank you for joining us today. My name is Jessica Lordy, and I'd like to welcome you to our webcast, How Open Source Big Data is Helping to Fuel the World Sustainably. Before we get started, I'd like to go through a few quick things. First, please do feel free to enter any questions throughout the presentation. We will be addressing as many of those as we can at the end of our talk today. Please also feel free to share this webcast or anything that you hear today with your social networks. We've included Flavio and Jeff's Twitter handles, as well as ProAgrica and HPC Systems on almost every slide, and we would definitely welcome your sharing. So today we've got two wonderful presenters for you. We've got Dr. Flavio Villanustre, who is the VP of Technology here at LexisNexis Risk Solutions, and he is responsible for the HPCC Systems platform. Flavio has been involved with the open source community for over 15 years. He also helped to start the first Linux group in Buenos Aires, and he has released several pieces of software under different open source licenses. We're also pleased to be joined today by Jeff Bradshaw, who's the CTO of ProAgrica Adaptris. Jeff is also the founder of Adaptris, and he's spent his career integrating data across a number of different industries. He's contributed to a number of international standards bodies, and he has worked with large enterprises to get meaning out of their data and to break down data silos and share data seamlessly across organizations. So you'll see several examples of that today in his presentation. With that, I'd like to hand it over to Flavio.
Thank you very much, Jessica, and hello, everyone. I'm very happy to be able to tell you a little bit more about our HPCC Big Data platform, and particularly I want to reserve most of this space for Jeff to present how we use this platform for this agro business. So without more preamble, let's go through a little bit of the history on HPCC. We designed originally this big data platform back in early year 2000. This is before big data was even called big data and before other big data platforms were out there. This came up of a need of LexisNexis Risk Solutions and RELX in general. And eventually, by 2011, we decided to make the platform open source. We really wanted to tap into the innovation that an open source community can bring to essentially any software platform. And we continue to put emphasis on the quality of the platform, on the interoperability, on the basing it on standards, and making it easy to use. And that is very, very important for us, having a consistent platform that can be easily leveraged to do data analytics and big data analytics. And particularly nowadays, some of the technology trends around, for example, Internet of Things. Throughout the last 6 or 7 years, we have been enhancing a number of community-facing tools. This goes beyond the platform itself, but also all of the collaboration tools, online training. We have massive open online courses for HPCC. They are all available online and free. And certainly everything that has to do with documentation and communication across. And the community has been driving a number of efforts, and we have really tapped into the community for innovation and defining the roadmap in the platform. Now, just to get everyone on the same page, I would like to tell you a little bit about the original problem that made for the inception of the HPCC platform. And the problem has to do with data integration. As you can see on the screen, when you get data from data sources that you do not control, the data is not as well defined and clean and properly structured as you would want. It is not textbook data. It has inaccuracies and it has errors. It has empty areas. And unfortunately, if the amount of data that you're trying to process is very large and or you have many sources of data, going over the data elements to ensure that the data is what you expect it to be is a very hard problem. So the core need that we have initially, and to which the HPC platform caters very well, is to deal with this data integration problem, essentially getting all of these data sources together. And as you can see on the right-hand side of the screen, all of these data sources with these inaccuracies inside can help solve some of these holes by exploiting the partial overlap that the data sources have. And certainly, once you have dealt with the data integration problem, HPCC is also able to do all of the data analytics on top of that, essentially transforming this base data, this raw material, into smart data, actionable data. The data that we typically see HPCC used for is now depicted as a funnel on the screen. And as you can see on the left-hand side, you may have different data sources, some of these structured, some of those unstructured, perhaps images, perhaps sounds, perhaps documents. And as you move towards the right, you can see the pipeline on the top going through a number of steps and understanding the data, which is data profiling, cleansing the data, standardizing the values and normalizing them, and certainly building the analytics on top of the data. As you move from the left to the right, the data volume tends to decrease because you are cleansing the data, you are increasing the density of information, and the quality of the data increases. And of course, on the right-hand side, you build any analytics and any search and retrieval solutions that you need to deliver from this data. And this is exactly what the HPC platform does very well. It has, and you will see on the screen right now, two main components, two main systems. One is called Thor. Thor is a batch-oriented system meant to do data integration. The other one is called ROXIE. ROXIE is a real-time, highly scalable and highly available data delivery system, an analytics delivery system. And both of these components, Thor and ROXIE, are programmed, are managed, are data workflows and data queries are defined using a programming language called ECL. ECL, we'll see later on, has a number of advantages over other data languages, and it gives this platform this cohesive approach to data processing. You don't need to have a number of different tools. You don't need to use a number of different languages. You can do all of this beginning to end, from your data ingest to your data delivery or your analytics delivery, with a single common interface. Now, to focus a little bit more on Thor, I mentioned before that Thor is a batch-oriented system. Thor is where typically your data integration process happens, but it's also the place where you can, for example, train your machine learning model. It's the place where you can learn more about your data. It's the place where you can discover elements in your data. All of these type of analytics typically are batch-oriented, for example, running a clustering process on your data. And Thor is specifically designed to leverage and scale across a cluster of commodity nodes, computers. Both Thor and ROXIE have that property, so you can run Thor or ROXIE or both in a single node, in a single computer, or in a virtual machine. But we can also run Thor across hundreds or thousands of nodes, and the same thing applies to ROXIE. In the case of Thor, all of the nodes will be used at the same time to run a single data process, which means that you can potentially tackle very large problems and sometimes very complex processing on those data sets, with very large data sets, in a very, very efficient manner. But ROXIE, again, is equivalent in the fact that it can scale across commodity nodes, and again, can run on a single computer or in a bunch of computers that are tackling the same type of data problem around typically data delivery, data retrieval, real-time analytics. But the specific capabilities that ROXIE brings to the table are those around high availability. Anything can fail and the system continues to run, and very high throughput, very low latency. So ROXIE can potentially answer thousands or tens of thousands of queries simultaneously with very low latency per query, which makes it especially well tailored towards problems like, as I mentioned before, Internet of Things, when you need to do stream processing and at the same time handle a large-scale data delivery problems. So your data can be large, can be very large. You may have petabytes of data that are available online. You may have complex analytics that you have built using Thor, and some of those potentially even using ROXIE. And you may have tens of thousands of clients hitting this system in real time to get answers from them. ROXIE exposes a number of standard interfaces. I mentioned our adherence to standards, and these are JSON, XML, RESTful, SQL interfaces. So pretty much any standard system out there can connect to Thor and ROXIE and access the data without pretty much no need for any glue, additional glue built. And I mentioned ECL. ECL is the common language to program these systems and to build data processes. With ECL, you can define what type of data workflows you want to build, what type of queries you want to deliver in ROXIE. And the particular approach that ECL brings to the table is the fact that it does it in a declarative manner. If you are familiar with SQL, you are familiar with the declarative programming language. SQL, you say what you want, and the databases will do what is right to get that action completed. And the same thing applies to ECL. But ECL is a far more structured language. It provides for a far better code reuse. It is easier to debug and troubleshoot. It is far more concise, and it is higher level than ECL, and gives you the ability to build fairly complex data processes and data queries with relatively little effort. The important concept that I mentioned before in the fact that the system can scale from a single computer or a single virtual machine running on the computer to clusters of thousands, hundreds or thousands of nodes running means that you can potentially start small with a system and grow as you need without needing to re-engineer your solution or change anything in your process. The property that ECL also has is the fact that when you code in ECL a data process, that coding doesn't require any knowledge of how many nodes or how many computers the system will run on. If you have a single computer, that process will run. If you have 1,000 computers, the same exact code will run as well. Now you will be able to do that faster and with a lot more data. But the system, it wouldn't be as powerful if it was only stopping at the layer of ECL. So on top of this platform, there are a number of additional tools and integration components that bring the ability to deal with more complex problems. I mentioned machine learning, for example, and other problems around data analysis and real-time services. And particularly interesting is the fact that it also can support code in other languages. If you are not familiar with ECL or SQL, but you are familiar with Python or Java or R or Spark, or you have data in Spark or Hadoop, you can use all of these different type of programming languages and systems to interface directly with HPCC. So you can get the best of both worlds. You get the productivity enhancement that HPCC brings to the table, and you get to use that language or system that you're familiar with, or that environment where your data is stored. So this can give you a fairly sophisticated and scalable system that doesn't require you to re-engineer your current solution in order to leverage. Now, without much more on this, and I want to reserve most of this space for Jeff on the particular solution from ProAgrica, I will pass the voice to Jeff. He has a great presentation. I hope you enjoyed it. Jeff, the floor is yours.
Thank you, Flavio, and always a pleasure to follow such a great presenter. My name is Jeff Bradshaw. I'm the Group CTO for ProAgrica Adapters, and obviously this is some of the stuff we've been doing in the agricultural sector using various parameters to kind of help people get more from less, really, in the agri space. So firstly, just the arbitrary background of who are ProAgrica is something that we tend to market by stealth, and our marketeers will probably kill me for saying that. But basically, we're a company. We have 4 areas within the business. First is the media. So we actually have magazines that farmers read. For any Dutch speakers on the presentation, I do apologise in advance. But one of our publications is Boerdery in the Netherlands. I can't say it properly because I don't speak Dutch. Or Farmers Weekly, as the UK version is known. We have software, so we actually have our own farm management software, which is kind of important to what I'm going to tell you about in a second. Obviously, integration and connectivity is close to the heart of our business. Dealing with data spread around wherever it happens to be, integration is a key part of that. And then, of course, most importantly for today's topic is really the data and analytics piece of what we do. So, why agriculture? Well, agriculture is the centre of the food chain. We like to eat. All of us like to eat, and by 2050, we've got to feed 9.5 billion people. Diets are changing. The diets in Asia now are much more protein heavy than they ever were before. Population is growing. Obviously, water. We have a choice of either drinking water or spraying it on crops. We have a choice of growing crops to eat or growing crops to fuel our cars, or growing crops to feed animals that we want to eat, depending on the diets and the things we're changing. And of course, the amount of available arable land is declining. The population increase. We need to house more people. We need land to do that. So there's a lot of pushes and demands, and of course you've got things like sustainability. You've got things like traceability as well. So what we want to know where it comes from. We want to know that the cow was treated with love before it was turned into a nice juicy steak, and what happens to that cow along its life cycle. But also, how can data help us? How can data improve ag? Because you always hear farmers complaining about the weather and complaining about oh, it's too wet, it's too dry, too hot, too cold. But actually, that's only less than a third, actually, of the factor behind the yield of corn, for example. Most of the rest of it is, what sort of hybrid you're planting, the fertilizers and nitrogen levels in the soil, holding the nutrients in. What was in the crop before? One thing we're taught in school is about the crop rotation systems, and also, how many plants we plant, how we plant it, and anything we put onto the crop to help it or inhibit growth. So all of these factors are kind of interesting, but it's actually getting all of the data and correlating it that is what we need to do to help us. So within our data world and what we're playing with, it's quite an interesting mix. It's quite an interesting area because you've got obviously systems that farmers use to manage their business. And largely they'll look after, what stock they've got on hand, what crops they're growing, what seeds they've got, what crop protection they may have, and all the kind of businessy things around the farm. Huge amounts of drones feeding data to the world. Obviously we have satellites as well, monitoring what's going on. We have things like sensors. IoT is a huge part of what we do. In animal farming, in field farming, you've got moisture sensors, you've got weight sensors, acoustic sensors, temperature sensors. Knowing what the soil's doing is also important, and soil sampling and pulling data in around the soil and using models around that sort of stuff. And then, of course, we've got more IoT, really, which is the machinery. Tractors emit data, sprayers emit data, planters emit data. Of course, weather is a key part of what we do. And then we have the B2B side of things, the manufacturers and distribution channel. So what's coming into farm? What can the farmer get to his crop when he needs it? And then finally, we have the doctors of the farming world, the agronomists, who help farmers by telling them what they can do and what recommendations, what things they should do to help them produce more with less, really. So just to give you a bit of a feel for some of the volumes of data that we're dealing with, there's about 570 million farms around the world, 25 million tractors, 50 billion chickens. The numbers are staggering, really, in terms of what we're dealing with. A cow, you're tagged to an individual actual cow, but a chicken, probably you're going to look at the flock as a whole. Also, we have different regulatory requirements. So, my favourite stat really is in the UK, and I was chatting to someone over dinner about this last night. Every single cow in the UK has a passport versus 39% of the US population. We can tell when a cow was born. We can tell every other cow it's interacted with throughout its whole life. And whether it's eaten grass in the UK or in Ireland, and what else it's eaten. And it's really important to be able to have that stuff for a level of provenance and knowing what's going on where. But again, it just generates so much data, and that's really the key of this sort of thing. However, one of the challenges we have, or probably the biggest challenge we have, is we're working with islands of data. A lot of the systems we work with in the agricultural space are written in VB5, deployed out on a farm somewhere that two guys in a shed happened to write in the 1980s. We've got lots of very old systems spread around the place, and that's where we need to get the data out to actually have value around the data. There are lots of those islands, lots and lots and lots. So integration and pulling data out is key to us in everything we do. The other thing is the data is very, very dirty. One of my favorite examples is where we one of the certain crop protection products out in the market. We had 1,000 different spellings of the same thing, as a really simple example. The one thing with farmers, they're great at growing things and great at feeding everybody. They're really, really bad at typing. None of them will get jobs in typing pools, fortunately, for the rest of us. The other thing as well, they don't always record everything. A lot of things are regulatory about what they'll record, but they might be busy. They care more about what's going on in the field than in the IT system at the back end. And did I record it? Well, maybe not. Or I might have missed something. So again, we have to be able to deal with the fact that the data we're playing with may be incomplete, and that can have consequences, of course. Just to give you a feel for some of the machinery data, a single tractor generates about 30 megabytes of data a day during the season. In the UK alone, there's 11,000. So that gives you about 160 gigabytes of data per day during the season, assuming only 50% of the tractors. That's an industry stat. It's not we've made up, and there's a vast area of integration around those devices because it's not just a tractor, it's a tractor plus a spreader or a tractor plus a planter. So there's huge combinations and variations in the data, and just getting that data somewhere where you can make sense of it is a huge challenge. So how have we dealt with this challenge? What have we done? How have we built this stuff? So effectively what we've used and some of the feeds we have into our HPCC, and you can see at the center of our platform is the HPCC and the components that Flavio was introducing and talking around earlier on. We use our own integration technology, Interlock, to pull data in. Now we're pulling data in from, as I mentioned before, the farm management systems. Also, we're using reference data. So, for example, soil classifications, soil type, soil quality, and those sorts of things. We're also using a partner of ours, Iteris, to pull in weather data and temperature data around the Earth. We have weather data to about 1 kilometre square. It is kind of one of those things, and being a Brit, we tend to talk a lot about weather. It's one of the main national obsessions, other than anything else. So weather is something we're quite passionate about, and obviously that's just imagine just getting 1 kilometre square weather data, historic and forecast. How much data that is just for the weather piece of the equation. Then of course we have the machinery data I talked around earlier on, and we're dealing with different partners and pulling in their data. And we pull that all into our core HPCC platform. And then we have the data science layer. So I mentioned earlier on about the incomplete and missing data. That's where our data science layer comes in and helps us, sanity check the data, fill in the blanks, and help us derive what's missing and put that back into our core big data platform. And then we're using search to surface the data. So we're pulling data out of our HPCC layer indexing it and allowing it to be available for search. Therefore, we can expose that via API to our customers with some enriching, and we can also use our visualization tools based around, again, access entitlements to make sure people are able to see what they're sharing, because ownership of data and who shares what with who is kind of sensitive. So that's an area we're quite keen on making sure we protect. So just to give you a bit of a view of our technology stack, obviously we're a big Linux shop. We use AWS extensively, and obviously Apache for the web servers. Our applications generally are kind of React and JavaScript type applications. Obviously Node.js is our API layer. And then of course, HPCC, Artifactory, we use Jenkins to automate a lot of our processing. Interlock, as I've mentioned, is our integration fabric, and then of course MongoDB for some of the other use cases around the patch. So just to run through some of the various layers, obviously our data storage and ETL layer is powered by HPCC. As Flavio mentioned before, it gives us a massive parallel processing capability, and we can scale the platform, the base underlying platform, very quickly. And actually, it comes bundled with the ECL language, which really is something that helps, and it's cluster aware. So, the load is shared across the nodes in the cluster. So all of our hard data stuff and the really big chunking takes place down in the HPCC. And just to give you a bit more on ECL, obviously, as Flavio mentioned earlier on, it's declarative. It's designed for data scientists by data scientists, really. It's very effective, very efficient. The stat we use quite often is, a single line of ECL code is equivalent to about 120 lines of C, and it's a lot easier to it's a lot easier to code ECL than it is to find C++ programmers who want to write loads of code, and a lot easier to manage and work out just at a high level very quickly what's going on, what you're sorting on, what your parameters are. It's really good at that kind of entity linking and cleansing of data, which is something that for us is very key. Linking entities together, knowing that this crop zone within a field is this crop zone within a field, because you happen to be a few meters into the field rather than to the edge, is really, really important for us. Knowing that it's the same thing and having context around that is something we can't ever underestimate. So if you look at the ingest side of things, obviously we have farm management systems, and these are two examples. Obviously Gatekeeper, we're slightly biased to because it's our own. And Muddy Boots is another one popular in the UK market. I'll cover those questions in a second. There's some good questions coming through at the moment. And so we're pulling data in. Now, the interesting thing here is, if we look at the Gatekeeper example, this is the version we're working with is a federated system. So it runs on farm with its own SQL database. What we're actually doing is pulling data in from backups, restoring the backups, extracting the data, and using Interlock to bring that in. So it's kind of taking deltas of databases, which is a huge thing. It's not just, and I can't overemphasize the point that, we're not always dealing with modern cloud systems. They're not mobile applications. These are legacy database-led applications that we're playing with here. So here's a bit of an example, some of the data, and we can view one of the cool things actually within the HPC environment. You can actually see the files. So here's a bunch of logical files that we've pulled in. So each of those contains a whole raft of data from one of our farm management systems. So next, we actually want to start making sense of the data. So one of the really important things for us is not every farm management system has a canonical version of the truth. They've all got their own schemas. Some of them have different versions within their different versions of products. Some of them are good, some of them not so good. Some of the products we work with have really tied down the ways they represent things. So, a product code is a product code. The name of a particular chemical, for example, and all the validation of all that sort of stuff that goes on. But we don't want to be tied by any of the farm management systems. They have their own data models, but we're doing a lot more. It's a lot bigger picture, so we can't be tied to what they do. So what we did, we started looking at the industry and seeing what's out there in the industry. And I was working with a team on one of the industry bodies called Ag Gateway here in North America, where we developed a standard called ADAPT, which is around machinery data predominantly, but it's a good starter for 10. So we took that as our base model, and extended it. And then what we do is when we ingest all the data, we convert it into our canonical model. So we have a common model, so it's a common language by which we can do some interesting stuff. Just to give you a quick snapshot of what our model kind of looks like, here's a representation of the model. As you can see, it's quite complicated. There's a lot of data there, and our data scientists absolutely love it. I'm seeing some really good questions coming on. I'm definitely going to get to those because they're quite exciting. So yeah, I'll come on to those questions in a second. Okay, so next, once we've got the data in the canonical model, we then need to make sure that the quality of the data is quite good. So that's where we run our data quality metrics. So to do that, basically we calculate a score. So for every crop zone, and the crop zone is kind of like within a field, we apply logical rules. So do we know the location of the field? Is it one we've seen before? Do we have the weather? Do we have the soil type? And do we have other data around that location? Each farmer is doing a number of operations on his fields. You know, he might be going out to spray pesticides or herbicides. He's planting, he's harvesting. So we like to know what coverage we have for that field in terms of operations. What's been done before to the field in this season, but also in previous seasons. And do we recognize what he's put on that field? Because obviously, certain territories we have regulatory databases we work with, so like Centric in the UK. We pull that data in as well to make sure that actually they are complying with regulations and that they're applying things they should be applying. So we do a bunch of quality checks on the data and sanity checking to make sure it's all good. So once we've done that, we've got our features ready for analytics. We can now start to use the data because we can score it, we know what's going on. So then we start to create the features. So for each operation, we want to know what the crop is, what the last known growth stage was, for example. So, you know, is it T1? Have they applied the appropriate regimen for T1? Where we are in the season, obviously when the operation happened. What type of operation? You know, sometimes it makes no sense that you get things out of order if they forget to record something. So you've got to make sure you can kind of start to get on top of those things to help you predict the growth stages and predict what's coming. Because then once you can start to predict the growth stages, it helps you then with giving the agronomist information about what's going on in that particular field and what type of product they're applying. So, you know, a classic example would be a farmer's growing a particular variety of corn, and he needs to protect against a particular disease based on certain conditions. So if the weather's been hot during the summer, the pests are more likely to survive. So then he needs to make sure he's applied the appropriate pesticide at the appropriate time. Otherwise, he could be influencing his yield. And ultimately, you know, a farmer makes about 14 decisions per season that has a material effect. But like most of us, they don't get that the instant gratification. You know, in most points in life, when you make a decision, the response is fairly instant. You know, did I remember to lock the car? You know, well, something may be stolen from the car if I didn't remember to lock it. But a farmer doesn't know that someone's stealing from his car until right at the end of the season when he goes to harvest and the yield isn't what he thought it was going to be. So we have to be able to help them and gather this information and enrich it. So then we go into our data science layer. Now, we've kind of done this slightly differently because when we built our platform, there's a lot of stuff that we needed that wasn't available in the core HPCC system. That's something that's evolving as we go along, and Flavio and the guys have taken a lot of feedback from us. We've worked very collaboratively with the HPCC team to feed back in what we're doing. But essentially what we do, we have our integration pipeline. We pull data out to you know, the feature set of what we're trying to play with, and then we go away to our data science layer where we actually start to apply the logic and do a bunch of stuff, and then spit the results back out, and then it goes obviously back out into our HPCC environment. So this is kind of like a little, you know, it can run any sort of query, and it just runs it over the pre-trained variables effectively, and then it's deployed. So our data science team can play around with the data, manipulate it, and then we just apply the rules across it as we need to. So now we've got all of the data in our HPCC environment. It's clean. We can start to visualize it and show people what we've got. So to do that, obviously, again, we use our integration fabric, and this process is all automated. So, you know, the change in the data when everything's been updated, automatically we'll deploy everything we need to bring the data out into our Elasticsearch and index it. and then obviously expose it via the website. So you can come into the Agility platform and see the widgets that we've built. And we are continually evolving and building new widgets to let people see what's going on and how they can do stuff. So here's what does it deliver? So what? The big question. And here's an example, one of our screenshots, and we can see here, we can see, crops that are growing, the soil types that the crops are growing in. You can see where they are in the UK, and this is obviously a UK example. But effectively, we're giving a full insight, a fully integrated data as a service platform. Someone can come in here and look at it, and we can slice and dice it differently. And depending on the user, so an agronomist would look at a certainly different value, or different set of widgets to someone wanting to see what's going on in the market. If I'm a manufacturer looking at what crops are growing, so I can start to move crop protection into the right areas to apply it when it's needed, this is a sort of dashboard I might want to look at and see how we go. And then we can start to give them end-to-end value. So there's value and widgets available for agronomists, for manufacturers, for the co-ops who are selling to the farmers, and actually for the farmers themselves. They can start to see, oh, hang on, I forgot to do this based on these weather conditions, for example. And we can give a full, quite detailed level of analytics off the back of it. And the whole, ultimately, why are we here? Well, we're trying to increase yield, increase profitability for the farmers, but also reducing, the cost. So reducing the inputs and reducing the environmental impact. So how much water we need and all those sorts of good things. So just to also, again, I like to show some screenshots. It's always tangible. We have a lot of data. I can't emphasize the volumes of data under the covers. And the visualization is a kind of handy way of showing people the sorts of stuff we have. But here's an example from one of the UK growers. You can see in the middle of the screen the operations that they're doing. You can see, obviously the environmental conditions in the middle. We can see the crops that are growing, what's grown previously in these crop zones, and also more detail. So what operations happened, when they happened, what was applied, and where it is. So there's a huge volume, huge amount of detail behind the scenes that we can draw on for these widgets. We can also present it differently. It's a UI, right? So you can start to do it and this is an example for an agronomist, where an agronomist is like a doctor. If you give a doctor the answer, they're kind of less interested in using the platform. It's about giving them cues. So here we can see, red lights where things haven't happened that probably might want to happen. A guy is growing a crop that's susceptible to a specific disease, and he hasn't applied the appropriate crop protection. And it's one of the farms that an agronomist is managing. So it's like a trigger to the agronomist. So actually, I may want to go and speak to that guy and see if he wants to apply some of this crop protection for me. And again, if he doesn't, what's the risk? Well, the risk is he might lose the crop or not have an optimum yield. Another example of the platform use is we can show market intelligence. So here's an example from Australia. And actually, this is slicing and dicing supply chain data to show by supplier market share. Actually, this is a high-level project we're just working on right now. But it lets the manufacturers work out where they are in the market compared to their peers. Who's selling the most, who's selling the least, where do I sit, how much of the market have I got in various territories, and they can then start to take action based on that and gives them more intelligence and more interest. So the arbitrary customer slide, of course, we've got lots of customers, about it's over 3,500 fully integrated ag customers, and they're doing obviously various different things. You've got guys in the animal health sector, guys, manufacturing companies, co-ops, retailers, input manufacturers, all the various bits and bobs. And lastly, I'm happy to open up to questions. I can see we have a few questions here. So certainly, how do we compare HPC systems? That's a really good question. So how do we compare HPC systems with other systems and infrastructures that we've practically used before? So we did do a prototype initially with one of the other major big data platforms and data streaming platforms from one of the large software manufacturers in the world, who I shall not name. But actually, it was really hard to work with. It wasn't as good at storing big data as HPCC. And I think once you get into using the HPCC platform, it's very scalable. It's very easy to use. It doesn't require a great deal of maintenance. We've not got an army of operations people looking after it really, and it's efficient. It does what it says on the tin. Very stable, it doesn't fall over. And the way we've architected our system, actually, even if we were to lose the core big data platform, that would only give us a lag in the data that we're playing with. It doesn't affect the presentation layer. We've separated it out to give us much more stability and availability. Next question I have here is, would a similar system be viable for supply chain management in general? Absolutely, 100%. Some of the example screens I showed you at the end, the market share stuff, is just looking at supply chain data. We do a lot of supply chain infrastructure. Our FRF brand is a massive B2B network. It's obviously specialized at the agricultural sector, but this is, a huge network effect. So starting to see, what stock is in what location is actually now viable, because you can sit this on top of the supply chain, see what you've got where, and that's a huge problem in the agricultural sector. If you look at the seed cycle, there's a 6-week window when the seed's sold, but you don't really know what you've got to sell before the start of that window. So it's really, quite an important one. Another question: how difficult was it for the team to learn and use ECL? Well, I think we did about a week-long course with Flavio and the team down in Alpharetta. If you've got data scientists and guys that are used to using, those sorts of languages, it's actually very simple. The tooling around it has improved greatly in the last sort of year and a half, 2 years that we've been using it in Anger. It's really good. It's not like a hard language. It's not like trying to take a SQL developer and say to him, right, go and learn assembly language. It's nowhere near anything like that. It's more akin to trying a slightly simpler variety of SQL, if you will. It's a much easier language to get your head around. So yeah, that's a great question, and absolutely. So another question here that came in earlier on: how much real stream processing, analytics, and alerting is needed in the industry, and how much is deferred in reporting? That's a good question, and it depends on which area of the industry. So a good example would be if you're trying to detect pests or risks to crops. That sort of stuff is quite real time. Or if you're trying to detect where products are in the supply chain. So if I need some crop protection because I've got an outbreak of a disease, then that's pretty real time, and I need the instant gratifications. So that's something that's really, really important. So we do need, it's a balance. Some stuff is by nature not real time, but a lot of it is actually as near to real time as we can get it. Absolutely. And it's not about, I always tend to think of deferred analytics and reporting as driving a car looking through the rearview mirror only, right? You know what's happened because you can see it behind you. You don't know what's, you're about to go into the back of a truck. So it's a balance, and some things you don't really need immediately. Some things you do, stock location, ability to find the appropriate pesticides or herbicides or fungicides, ability to find the seed that you need to get in the ground when you need to get it in the ground. Some of those things are very, very small windows that we need to process. What else we got here? So is the software tool set stack really open source? So yes, it's a good question. Obviously, HPCC is open source, and everything we use within the HPCC environment is open source. Obviously, Elastic is open source. Our interlock adapters, the core framework is open source. There are obviously chargeable modules. Out of the box, we have the magic number is around 311 pre-built application adapters. So if you have data that's in things like SAP or Oracle or any of the kind of off-the-shelf applications, or you need to deliver it over random different COM standards, then those are modules we have that we would charge people for. But the vast majority of the stack we're using is actually open source, and it's available. And, feel free to reach out if you need any guidance and help on that. Certainly we're more than happy to help other people with our platforms and build other platforms. The integration of Elasticsearch was not difficult because we have that within Interlock out of the box as a platform. So that is something we do in Anger, not hard. And we do a lot of prototyping as well. So we do a lot of prototyping with Elastic and Kibana before we start to invest and build in the widgets. Again, for us, it's simple, just configuring the Interlock adapters to pull stuff out, stick it into Elastic, and away you go. So it's a very, very quick and simple integration flows. That's what we do. Where are we now? Where is your open source code base? So the Interlock stuff is all up on GitHub. Feel free to just drop us a note or tweet me, and I can give you a link and let you have a look at that stuff. That's available. The machine learning module of HPC systems. So we haven't used that in Anger because really it was early on in the days when we started building that machine learning capability. We were ahead of the curve a little bit, and that's something that my technical team and I are feeding back to Flavio and the team in the HPCC group, and kind of helping them move along. So we are working very closely with the core HPCC guys because it's something we've built and learned and got the scars, and we're happy to share. So that's quite a good thing. So scale of our current cluster. Oh, it's not that big actually. It's how many nodes have we got now? That's a good question because I can't remember off the top of my head. It's not a massive. It's not as big as the ones that the HPC use within other areas of the business. We've probably got around sort of 20 servers, I would suggest. Probably not more than that at the moment. But it is growing as we're getting more data and more of the machinery data in. Obviously, the usage is going up, so we're growing the cluster in line with the business requirements. I think that is all of the questions. If anyone has any more questions, feel free to ask, and of course you can always reach out, tweet me. I'm available. Feel free to reach out and ask more questions.
Absolutely. So we'll stay on the line here for a few more moments. And while we're waiting for any additional questions to come on, I'd like to remind everyone that under the Attachments tab, you should have a copy of this presentation, as well as links to several different things within, let's see, so we've got the HPCC systems link where you can go in and you can certainly find this case study, but also the free training that Flavio referenced and more information on the HPCC systems platform. There's a link to the ProAgrica website where you can find out more information about ProAgrica and everything that they offer, including media, software, integration and connectivity, as well as data and analytics. There's also a link to the Agility platform, which Jeff spoke about, and the F4F agricultural e-commerce platform. So a lot of wonderful information there on ProAgrica if you would like to learn more. Let's see. I don't see any more questions coming in. So I'm going to go ahead and wrap this up and thank everyone so much for joining. We appreciate the time that you took to watch this presentation. And please do reach out to either Flavio or to Jeff if you have any questions. Both gentlemen are very open and willing to answer any questions that you might have. Thank you so much.
Thanks for the time, everyone.